Good morning, good afternoon, and good evening to our participants from Europe and Asia. Hello, my name is John Chan. I am from the Communications Group at Freeslate. I will be your host for today's webinar. On behalf of Freeslate, welcome to the first webinar in our series on high throughput research in the area of small molecules. Before we get started on today's webinar, I would like to go over some logistics. During the course of the presentation, you're welcome to submit your questions via the Q&A console on your webinar interface. We'll collect those questions. At the end of the presentation, we'll answer those questions verbally in our Q&A session. We will now move to the technical presentation. Today's webinar speaker is Dr. Pu Sun. Dr. Sun is a senior research scientist at Freeslate. In that role, Dr. Sun conducts high-throughput reaction screening for clients in the pharmaceutical and chemical-related industries. Specifically, he examines optimization of important organic transformations such as asymmetric hydrogenation, cross-coupling, and nucleophile addition. Dr. Sun received his BA degree in chemistry from Hanover College in Indiana. He then moved to Penn State University, where he did his doctoral work with Professor Stephen Weinreb. The focus of his PhD thesis was on natural product synthesis. In his free time, Dr. Sun is an avid table tennis player. Recently, he placed second in the Freeslate table tennis tournament. Since that time, he has been in practice intensely, looking forward to next year's tournament and winning next year's event. Dr. Sun?
Thank you, John. So, before I get into the talk, I would like to introduce Freeslate briefly. We are a spin-off from Symix Technology. So even though our company has been in existence for only about a year and a half, we have been practicing high throughput and microscale technology for over 16 years. We have over 60 scientists, engineers, and software developers within our rank, and our headquarters is in Sunnyvale, California. And within our small molecule service group, we provide high throughput service to pharmaceutical and biotech firms that include high throughput reaction screening. Like John said, that include such reactions such as asymmetric hydrogenation, CN coupling, and other type of transformations. Now, I'm going to get into my talk. There are two main segments within my talk. First, I would like to introduce our integrated and automated approach to high throughput reaction screening. Within this segment, I would like to talk about how do we approach high throughput reaction screening scientifically and operationally. Second part of my talk will be focusing on making sterically hindered phenols. Through high throughput screening, we discover a ligand-free condition that works very well. And finally, I would like to summarize my talk and do acknowledgement. Okay, let's talk about our approach scientifically. The first thing we'd like to think about is when you get a project, you collaborate with our client. So how do we define what we want to do? What's the issue here? What's our research goal? Mainly, there are two main possibilities. One is exploratory, one is optimization. Exploratory mainly means it's a new route, new idea about making something, and it's more like a feasibility study. But most of the time what happens is that the chemistry has been done on benchtop for a while, so we do have some yield, and some condition has been discovered, but we would like to have higher yield or EE. A lot of times, especially for final product, such as API, we want to eliminate any kind of impurities or at least find ways to reduce it. And certain other times, because of the condition has discovered so far is too costly or the solvent is not suitable, a lot of time it does have patent coverage on the particular transformation. We want to avoid all these situations. So after we actually understand the goal of this research, we can start thinking about doing a comprehensive review of this particular transformation. The starting point is always what we have known so far, especially the bench chemistry we have done. And the second step to this is to go out and look for patents and literature to see if there are any similar work have been done as well. The closer we can find within patent literature that resemble the transformation in question, the better chance we have in succeeding through high throughput research. After this, we can start thinking about putting the reaction variables together, what kind of condition you would like to screen. But there are two more factors involved in here. One of them is the scientist know-how and intuition. That means a lot of times scientists actually would like to have condition screened, but due to manpower limitation or just they don't have the time, so you never get a chance to do it. But now we have all this space open up for them to screen it. And then finally is the chemical availability. A lot of time you find a good transformation within the literature, but when you look for it, it's really has not been commercialized, which is we can't really screen them. I would like to emphasize chemicals availability a little bit more in the next two slides. So chemicals availability and selection is actually very important. So a comprehensive understanding of what's available is a prerequisite for our screen planning, because that's the options we have in terms of real screening. Now, what's in the literature is what we can get hold of. Within Freeslate, we actually have a lot of commercially available ligands, metal precursors, base, solvents, additives that's common for reactions such as cross-couplings and asymmetric hydrogenations. To illustrate, I would like to just briefly talk about how do we actually select chirophosphorus-based ligand. There are many advances that have been developed academically and even within the different companies. A lot of them have been commercialized, and you can get them through a variety of vendors. So what we have done here is we look through all of them, and then we group them based on their structure, diversity, and their capability. Here, the next slide, you actually this is how we group them. I mean, we group them into 9 groups. Certain groups have a lot of more substructures than the structures, and certain other groups that because they're fairly unique, they only have few in them. I would just like to mention briefly about a few of the classes. For example, the monophos type of ligands on the upper left, which is from DSM, and the BioNAP type of ligands, biaryl ligands from Takasago, or a lot of other companies provide similar structure biaryl class, and the ferrocene-based class from the lower left from Soviets mainly. So pretty much there are definitely a lot of people providing this chirophosphorus-based ligands. And there are 157 so far, but for sure they're going to be growing field in this particular area. Okay, now let's get back to how do we define a reaction. How do we define reaction variables? So like what we said here is we need to understand what the screening goal is. For example, if certain catalyst ligand class we don't want to screen because they have patent coverage, we don't emphasize that aspect. So we do a comprehensive review. We know what's available, and we talk about what scientists want to put into it as well. And then we can start putting a rough layout together in a library format. For example, this is just a simple example. For example, we decided we want to screen 3 catalyst precursors, 4 ligands, and 8 solvents. We can have this rough layout in this 96-well plate format. For example, for 8 wells, for 8 different solvents, we have 8 rows, and for the 12th column, we split between 3 catalyst precursors and 4 ligands. The actual design can be more complicated. It doesn't have to be this type of factorial. It can be segmented. It depends on what you want to screen. A lot of times, what we want to do is actually put a known condition that has worked on the bench and introduce into the wells to make sure that this particular well run well, because that should be replicated. I'll actually talk more about known conditions, how we do this as well. But this will actually make us comfortable, make our clients comfortable that the whole plate run as planned. Okay, so now, I'm going to skip a major part, which I'm going to talk about a little bit later, is operationally. See, now we have all the ideas settled. So what we actually need to do is to run the plate. So we call it, we have to do it operationally. So that will involve preparation, execution, and data analysis, which I will talk about a little bit later. So, okay, after all that, we get results from our first plate screening. So what do you do here? There are 2 parts. There are 3 parts. Like the 2 parts I just shown here is, for example, there's no hit, and then we decided there's no directions we can follow on, so we abandoned the route. A lot of times we do have hit landscape, so we can select certain hit conditions we would like to scale up to see that particular condition can be replicated under with a higher amount of starting material. And so, but a lot of times what happens is we would like to have follow-up screening as well. What that means is, we get a direction. We kind of see the trend. A lot of times there's additional variables we cannot actually include in our first plate. So we want to just continue add that into the follow-up screen. And we can eliminate certain variables that doesn't really perform well. You're more confident it doesn't really work. And we definitely focus on the directions where the variables that play more important role in this particular transformation. And in terms of reaction conditions such as temperatures, pressures, and reaction times, you can sort of see a lot of times the hit conditions is good, but the starting material remains. You might want to just heighten the reaction temperature to make sure you push it. But a lot of times you start seeing unacceptable amount of impurities, so you might want to lower the reaction temperatures to make sure it doesn't become a big problem. Some other times, you want to the reaction works pretty well. So the second plate, you want to just lower the catalyst loading a little bit, because eventually you want to have a process with the least amount of catalyst needed, and sometimes the higher the reaction concentration, the better for optimizing reaction process. So after all this, we can start planning our follow-up screens. Okay, so now we kind of talk about what we do this scientifically. So there's many type of reactions we have screened here within Freeslate. The 2 main things we have done is, I think is pretty common for everybody, is CX coupling reactions like CN coupling reactions, and hydrogenation reactions such as asymmetric hydrogenations. But if you kind of categorize the things we have done here what type of reaction we have done here, we have done aromatic electrophilic substitution reactions like Friedel-Crafts reactions. We have done aromatic nucleophilic substitution reactions such as the CC coupling reactions, so I'm going to talk about during the case study. We talk about aliphatic nucleophilic substitution reactions such as SN2 type of reactions. We have definitely done reduction type of reactions such as hydrogenations. So what kind of scenarios we have seen within the screen we have seen? So the good ones, we have seen dramatic yield or EE improvement, or a lot of times we see we have find less costly alternatives. That means either we actually find a route that is more economical viable, or a lot of times we find the reagent that costs less than the original condition. In terms of impurity, the impurity can be minute amount of impurity, such as 1 AP% or even less can be tracked. And the conditions sometimes is really high throughput is very suitable. You just vary the conditions and you actually discover conditions that can reduce its presence. And a lot of times we have new insight into reaction mechanism because we have 96 different conditions and then you analyze the spectrum. You actually have more insight into how this reaction works. And a lot of times the interesting trend can be spotted, such as solvents, solvent polarity will play interesting in terms of yield, and it doesn't have to be the one you think it will work. And the last but not the least is the ideas or the new route that people come out with doesn't really work that well, and we abandon them after a broad screening. Okay, so this will conclude my scientific aspect of a high throughput reaction screening. And so now let's talk about it operationally. How do we actually do it? So there are three main parts to this. There's a preparation, execution, and data management analysis. So you want to prepare things such as you want to prepare some analytical method, you want to do a test run, and you want to have a plan. For example, if you have 96 reactions, you have to definitely plan them. We use this software called Library Studio to plan them. And after you have done all the preparation, then we have to actually run the whole plate, which we use Automation Studio and Core Module here, which I'm going to get into details. Specifically, I'm going to talk about solid addition, which might be interesting to a lot of people, and the pressurized reaction, which might interest a lot of people. And after all this, there's a lot of data get collected, and how do we actually do the analysis? So first, I would like to talk about preparation and planning, pre-screening, preparation, and planning. So in terms of pre-screening preparation, the first thing I can think of is analytical method. Because a lot of times when you do receive a project, there's an existing analytical method already. But most of the time what happens, for example, LC we use LC all the time, and the original method tend to be relatively long. 20 minutes is very standard, sometimes up to 40 minutes or even longer. But if you multiply that by 96, it becomes a really time-consuming situation here. A lot of time what we want to do is you work up the plate, you set up the analytical method before you go home. Hopefully the next day you actually have results, sitting there waiting for you. So most of the time what we want to do is shorten the LC method if possible. For example, if you can shorten a 20-minute method to a 6-minute method, it becomes an overnight run. So you will have all the analytical data waiting for you the next day. Another thing is the workup protocol. So you set it up, which I'm going to talk about later. And one thing we need to make sure is we need to sample all the wells and be confident the sampling is truly representative of our reaction composition, so you understand what happened in each condition. And the traditional methods such as aqueous workup doesn't really suitable for this type of microscale situation. So a lot of times what we do is we have different sampling protocols. I'm just going to mention a couple of them. The easiest one is if you're confident all the reaction composition you care about is soluble in the reaction solvent, so we can actually just do direct sampling and the dilution for LC analysis, for example. A lot of time what we have to do is we know the solvent will not be soluble, will not dissolve everything, so we need to add a stronger solvent to ensure full solubility. A lot of time, because the volume is limited, we actually want to evaporate the weaker reaction solvent first before the stronger solvent is added. Sometimes we do add acid base to ensure the reaction is quenched at the same time. So after all this preparation, sometime what we will do is we'll do a test run. The purpose of test run is to replicate known conditions that during the bench chemistry, You see if it can be done under microscale conditions. For example, the bench chemistry can be done hundreds of mg to even gram scale, even bigger a lot of times. So you want to see if you can reduce that to mg scale. For catalyst, ligand sometimes is much lower loading, is much lower amount introduced. And see if you can replicate the condition. Also, the purpose of test run is, which is important for a lot of, not maybe for CN coupling, which is very common, but for other novel chemistries, we want to know, for example, we want to walk through the whole process from the reaction setup to the proposed workup we just talked about and the analytical we just developed to see if the whole process will work as planned. So, okay. So this is a screening planning. Another part of the planning is to actually do the planning for the real plate. For example, I'll use the same example again, 3 catalyst precursors, 4 ligands, 8 solvents. So all this can be prepared as a stock solution. As you can imagine, we need to add the desired reagent into the desired well. For example, A1 well, you want to add ligand 1, solvent 1, catalyst 1. So all this need planning. So what we do here is we use the software within Freeslate called Library Studio, which will help you to plan the whole experiment, including all the reagents, all the variables, and all the calculations, including all the stock solutions that you need to prepare for the final addition, and the experimental conditions, and the whole workflow, what to add first, what to do first, what to do later. I'm going to give you a more detailed description during our case study. So, okay, after all the Library Studio design, so now we're ready to do the real plate. And in addition to that, I'm going to talk about the solid addition and the pressurized reactions as well. So in terms of doing the real plate, so now we have the planning done through Library Studio. So next thing is Library Studio is a software. So we want to move this part of the software to another software called Automation Studio. So that means you export all the necessary information you need to the Automation Studio. Automation Studio do many things, but in this case, it takes all the necessary information, and which will control the hardware later. So, for example, I just a very simplistic diagram here. As you can imagine, this the reaction plate in the center with 96 wells, and the stock solution on the right. And you pretty much, you need to plan everything to make sure all the stock solution will add to the design wells according to your Library Studio design. The Automation Studio will take care of that. And then after that, the Automation Studio will do all the control. It will actually control, in this case, a core module, which is the hardware. The core module will listen to the Automation Studio and do liquid and solid additions and the reaction conditions at like the heat temperature, time, and the monitoring such as that. But for the pressurized reactions, we actually have another equipment called SPR, which I'm going to talk about a little bit later. Okay, so that's how we actually do it. But in terms of actual operation, I think people most interested in maybe how do we add solid. The simplest one is to solid that is soluble in the reaction solvent. In essence, that's become a liquid addition. You pretty much dissolve the solid in the reaction solvent and add it. Here, I will actually have a small clip just to give you some visual ideas how this works. As you can see here, is the syringe is taking up solvent from the stock solution. In this particular case, it's up to 1 ml. You can see on the upper right, you see the syringe taking it up, and then it will add to the well that you have designed in the Library Studio, the amount that has been all calculated, and they just add to the one that is needed. So we'll add either it doesn't need it anymore, or the needle syringe out of volume will go back and take up more. Okay, so this is the most simplistic situation. But there's other situations where the solid is not soluble in the reaction solvent. So what you do is you actually dissolve in a different solvent, which is soluble, but it has low boiling point. So you still do the solvent addition I just shown earlier, and after that you actually evaporate the solvent before the next step. So this particular gadget here, we call it Murphylizer. Essentially, it's you blow a gentle flow of nitrogen on top of all wells, and within 15 minutes, most of the solvent will just dry up, just evaporate it. So then what remains is the solid you actually want to add. Another situation, a lot of time when you actually do CN coupling reactions, inorganic base is essential. And here we cannot really, there's no organic solvent available that is, we can add. And so we have to add them in solid form. So what we do here is we do it in a slurry addition. It's pretty much, we'll do here another clip. I'll show you. As you can see here, it's vertexing the slurry. The slurry has the base here has been grounded and sieved for better slurry, and the vortexing is 1,000 RPM. Will have a very nice slurry. You pick up the solvent with the solid in it and add it to the design wells. You only can do it one at a time because solid will settle on the tip of the needle. So you only do one at a time. And after that, we'll do the same thing. We do evaporation, and the solids remain in the reaction well. And then finally, we have this instrument here called Quadernium. In this particular case, there's no solvent involved at all. So as the picture here show you this thing, shiny object, we call it hopper. So all the solid you want to deliver is contained in this hopper, and it will go to your designated well as planned in your library studio, and it will actually dispense it as planned. If you want to know more about Quadernium, you can always check out our website. Okay, so now we'll talk about solid addition. Other aspect of it is the pressurized reaction. How do we do pressurized reaction in a high throughput fashion? Here, the two first photos I show you here is how do you set up the plate. Imagine regular plate. There's it's pretty much essentially the same, but there's no holes throughout the plate. Here, there's a pinhole plate, and there's a gasket, and there's Teflon sheet. They all have holes on top, which will have hydrogen access. So all the wells have hydrogen access. So you put them together, and after the plate, so you add all the reagent necessary, and it will happen in the glove box. And then you put this into the reaction inside the reactor. As you can see, the reactor here is very heavy-duty steel. So you put it in, you screw it tight, and then you can move that to the SPR setup we have. The next picture we will have the whole SPR setup. So SPR pretty much do two things. It can heat, and it can pressurize to whatever the pressure you want. And what we'll do is to vortex it as well for stirring. So hydrogenation after it's done, you purge it, cool it, purge it, and then you can open up and you sample as usual. Okay, so now we've done all the reaction screening. So what do we do now is we have to actually manage. We have a lot of data generated. How do we analyze the data? So like what I said here is a lot of data coming out of from the very beginning, like when you plan the reaction, so Library Studio will generate a lot of data about each well, what kind of condition it has for each well, and Automation Studio, which is encompassing in terms of it will control both the core module, the SPR I show, or any other analytical instrument you have in the lab, and it will collect and consolidate all this data in the central database, which is very helpful in terms of tracking every aspect of every well. after the data is collected, and then so now we need another software to analyze it, organize it, analyze it, visualize it for you to have directions we need for the next round of screening or to understand what happened. The two software we have here is called PolyView and the Spectral Studio for different purposes. But in essence, what we want in terms of software environment is we actually want to have an integrated software environment which will encompassing the whole entire experimental process from the very beginning, the design, to the execution and the collection, and in addition, analyzing the data, presenting and sharing the data. If we have that, it will be very helpful for us to get a good grip about what the whole reaction screening. So this is conclude our first part of our talk. So like what we said here is Freeslate has scientifically and operationally, how do we do high throughput reaction screening? Another way to look at it is if you want to have a successful high throughput screen planing, we would like to have both very solid sound science in combination with integrated software environment and a robust and flexible automation hardware as well.
At this moment, we'll take a quick 2-minute session break. This is a good opportunity for you to submit questions on the previous subject matters. We'll also ask you 2 short survey questions. The first question is, do you own high throughput research equipment today? To input your answer, please click on the right choice and then hit the Submit Answer button. The next question is, do you plan to practice high throughput reaction screening in the future?
So let's get to the second part of our talk here, is to have this particular case study involving synthesis of sterically hindered phenols. So the goal here, as you can see, is you have this unprotected phenol and the ortho position on the right. We would like to introduce a variety of substitutions R double prime, and cross-coupling chemistry is very suitable in this case. Especially, we would like to have very sterically hindered substitution at R prime. And if the phenol can be unprotected, it will definitely be desirable because you eliminate 2 steps. So originally, this chemistry has been tested extensively in the lab, benchtop chemistry. The first type of chemistry we tried is negation coupling. In this case, non-protecting group is needed for this type of chemistry. And in addition to the protecting group, which is what we want to eliminate, the zinc chemistry is actually fairly sensitive. A lot of times, it depends on the batch of THF we use. The yield vary dramatically, so it's very touchy. So we move on, still a bench chemistry, to see if Suzuki coupling will work here. In this case, as you can see, the phenol is not protected. The chemistry works very well up to certain size in terms of R double prime substitution. If you want to introduce very sterically hindered substitution, it did not work. So high throughput screening is very suitable to search for alternative conditions to introduce sterically hindered substitution at the ortho position. So the first batch of high throughput reaction screening we did is using Suzuki coupling. Here we want to introduce this triisopropyl trip group to the ortho position. So within Suzuki coupling, what we have done is we have done two-plate, 192 conditions, reaction variables including catalyst, precursors, ligands, base, and solvents, typical conditions variables. But the best yield we can get is 5%, which is definitely not satisfactory. So like what we say here is, like what I said earlier, we abandoned this route with confidence that Suzuki coupling is not suitable for desired coupling reaction. So the next thing we try is Kumada coupling. Kumada coupling involves Grignard. So because of this Grignard and we don't want to do phenol protection, the first step we did is to depronate it using sodium hydride or a methyl Grignard. So after the depronation, so we for that particular plate, we actually use two opposing steric demanding Grignard. One is simple phenol Grignard, and another one is trip Grignard, which is the one we actually desire the most. As you can see here is the reaction variable setup is we have starting material. I highlight the amount of starting material we use so people have idea how much we run per well, and all the other things is based on this limiting reagent. And overall volume of the reaction is 200 microliter. The starting material is 10 micromole. And as you can see here is we use two base to depronate it, two Grignard, three catalyst precursors with two palladium, one nickel, and solvent we use only one solvent THF. And the reaction condition is shown here. And within ligand, we use 7 ligands plus one condition that does not have set condition does not have ligand involved. So after all this, like what we said earlier, we do a rough layout to put it on paper to see how do we lay out a 96 8x12 plate. As you can see here, there are 8 rows of 7 ligands plus 1 ligand-free conditions, and 12 columns involving 2 Grignard, 2 bases depronate, and 3 catalyst precursors. So after you do the rough layout, so you use Library Studio to help you to plan for the real thing. So in this case, you will have all the chemicals inputted, and they will calculate the stock solution needed. You tell them which well has what in it, and how much stock solution for different ligands, how much do you need per. Everything is planned within Library Studio. So one aspect of Library Studio is the workflow. How do you actually do it? In this case, I just did a screenshot, and then so people have ideas exactly how you run it. All this information will be exported, like what we said, to Automation Studio for you to run the real thing. If we go through this very quickly, so if you look at this recipe, we call the recipe, catalyst precursor is added first, followed by ligand addition, and followed by a starting material addition. In this case, you prepare them either in sodium hydride salt or methyl Grignard salt. And then you would do the Grignard addition, involve the phenyl Grignard and the trip Grignard. And this is a reaction condition here, 50 C, 12 hours. And finally, after the reaction is done, what we do is do the crunching, the workup, and the GC analysis. If you can see it, you actually use methanol to quench it, and then you evaporate the methanol, use toluene to dissolve everything you need, and then do the GC dilution, and then do the GC itself. Okay. So after everything is done, the analytical data is coming out. So we use this program called PolyView to analyze it. Here I just have this library view of all the GC spectrum. So pretty much give you ideas about all the data is collected. So you can sort them and visualize them and then analyze them and compare them if you want to. Okay, let's get to the data analysis part. So you have the first group I want to analyze is the phenol Grignard. So the less sterically hindered Grignard addition. So you have the sodium hydride base on the left and methyl Grignard on the right, and you have 3 different colors which represent different catalysts. And as you can see here, is mainly you have ligand B and a ligand D working pretty well, and the palladium works well, and the nickel work well for certain conditions as well. But more interestingly, if you go to the next slide, take a look at the next slide is when you do the trip addition. Here, so what stands out immediately is the column on the very right. So this particular condition, you have no ligand, is a ligand-free condition with sodium hydride as a base to deprotonate. There are conditions that, so with palladium ACAC, we do not need any ligand to have good or even better yield. So this is definitely something pleasantly surprised to be discovered. So next, what we want to do is to see, okay, so there's active conditions we don't need for ligands. So we do the follow-up screen with ligand-free conditions. So here's all the variables. As you can see, we use sodium hydride as a base, and we try a variety of different catalyst precursors involving 3 different palladium, 1 nickel, and 2 iron. And the Grignard, we vary the sterically demand for the Grignard from the least sterically demanding to the most steric demanding to see if there's trend in terms of how well the ligand-free condition will work in that subset. So if you take a look at the data here, the trend is pretty clear. So the Grignard is less steric Grignard doesn't really work well. So when you go up to the most sterically demanding Grignard, it works very good, especially with all the palladium catalyst. And so then we'll do another follow-up. So okay, so the palladium work well. So how about palladium chloride? So that's definitely the cheapest form of palladium. Just for fun, how about nickel chloride? So if we can use nickel, it will be even better. So as you can see here is we actually tried 2 different catalyst precursors, and the base, we expand the base a little bit. Lithium hydride and the trip Grignard is pretty much, we just don't add additional base, we just add more trip Grignard to see if what role they'll play, and 3 solvents as well. As you can see here, the sodium hydride again did very well consistently, and we pretty much stick with this particular base. So finally, what we did is scale up this optimized conditions involving sodium hydride and palladium chloride. In this particular case, we use microwave conditions to speed up the whole process. So the whole reaction can be done within 5 minutes. As you can see here, the 94% yield is isolated, is bigger scale. So to summarize this, to add a sterically hindered substitution, we have discovered conditions that we do not need to protect the phenol, there's no ligand needed, and the palladium chloride as the least costly palladium works great, and the condition we discovered can be scaled up. So this will actually conclude my talk. To summarize as we said, in order to have a very successful high throughput reaction screening, it requires both sound science and in combination with integrated software environment that spans the entire experimental process, and robust and flexible automation hardware, which will help us to deliver the reagent we need. If we can do that with high throughput reaction screening the right way, what we will discover is we can screen a broad set of experimental variables in a rational and systematic way, we'll be able to see the big pictures more clearly. That also means we can abandon the disadvantaged route with confidence, so we can focus on the more viable route. We can pinpoint or lead us to the more optimized reactions, and we can maybe serendipitously discover clues we might miss if we just only do a traditional benchtop chemistry. And finally, because of small scale involved, we will have preserved a lot of precious materials along the way. Finally, I would like to acknowledge all the chemists involved. There are many chemists involved in terms of developing this phenol chemistry and involving the high throughput protocols. Especially, I would like to thank Jim Longmire, who is instrumental in terms of developing many crucial technologies we have talked about here. In addition, there's countless effort by our engineers and the software engineers that designed, built, and perfected the hardware and the software that enabled us to carry out the high throughput research. We'd like to thank them as well.
Thank you very much, Dr. Sun. That concludes the technical part of our webinar. We'll now have a question and answer session to answer questions from the audience. Before we get started on this part, we'll take a quick minute to ask you 3 short survey questions. First question is, how do you rate the webinar on a scale of 1 to 5? Please select the appropriate choice and hit the submit answer button on your screen. Next question is, what improvements to the webinar do you suggest, if any? And finally, do you see the value in an integrated high throughput research solution towards reaction screening? Okay, so we have a good number of questions from the audience. We'll take them in a chronological order. The first question from the audience is, what is your average screen size in terms of number of reactions, Dr. Sun?
So a lot of times when we talk with our clients, we will try to, especially for the first round of screening, we want to do 96, to come out with 96 different conditions we'll propose. Like what we said, we'll look for patents and literatures and also talk about what they want to screen. And we tend to try to get the 96 plate. And then the follow-up plate, most of the time is 96 wells as well. But if there's definitely there's more focused screening, we can do a subset, like half a plate or whatever the number you want. It's very flexible. Library Studio will help you design whatever you want. And that's pretty much, yeah.
Okay. The second question is, during your screens, do you routinely obtain a single sample or multiple samples per experiment?
We do, the final workup is one sampling, obviously. But if you want to sample, we actually do sample during the reactions as well. But in that case, a certain sampling technique like evaporated reaction solvent will not work because you still want the reaction to run afterwards. So what you do, for example, if you want to do a coupling reactions, you have to pretty much sample it, slurry sampling. You just slurry it out and then dilute them. And if there's inorganic base involved, you just centrifuge them to pack down to the bottom, and then you do the dilution. So to answer that, we do sample in the middle if needed, just to see. It's not going to be 10 sampling, which is you have to think about the analytical involved. So if you just want to do one sampling in the middle, it's definitely doable.
Okay. The next question is, do you have libraries of reagents in place for all of the transformations described?
So, the common ones, we have the common reagents. But a lot of times, people want to have more unique ones than we order them. We don't have everything. I mean, there's a lot. And so there's definitely common sets we do have. We tell them that's what we have. And if we want to prepare, if there's more newer reagent, new in terms of we don't have them, and we can order them just to, they'll take a little bit longer to prepare the initial planning before the screening itself.
Okay. The next question is, have you ever done an amidation screen?
Absolutely. 100%. I can't mention more, but yes.
Okay. And then maybe we can go into a little more detail here. Besides the main reaction types such as asymmetric hydrogenation, cross-coupling, what other major reactions type have you done? Maybe just to name 3 or 4 to give the audience an idea.
Yeah, so we have done Friedel-Crafts reactions with a lot of Lewis acids. We have done nucleophilic substitution reactions like the SN2 reactions, which is not even, a lot of times it's not even catalyzed reactions. And, but it's a reaction screening. It doesn't have to be catalyzed. You just have come out with enough variables, and then you just screen them, catalyzed or not.
Okay. The next question is, can you set up a screen and walk away without worrying about mechanical or software errors? In other words, can you just walk away and not worry about or not have to be present during the run?
We tend to stay there because there's always, potential issues, glitches. I mean, it always happens when you're not there. And, the setup doesn't really take that long. So it's, to answer your question, yes, we do stay there when the setup is happening. We want to make sure, sometimes, there's just issues pop up. There's certain times the whole arm will stall a little bit, and then you just say, okay, then it happens. It doesn't happen often, but it only happens when you walk away. So you pretty much stay there to make sure everything ran according to plan. But it doesn't really take that long. So it does take some time. It's not, but we do stay around.
So, for example, how long would a typical run will last?
So, depends on complexity. If it's only liquid addition, like what we said here, it's definitely a little bit faster because it's sequential. You take a volume, you just add to wells as designed. But for the solid addition, for example, slurry addition, because one at a time you had to rinse it, it come back. So for solid addition, it definitely takes a little bit longer to do.
Okay. Next question. Do you conduct stability studies ahead of time to determine if your LC diluent will degrade your reactant or products?
That's definitely one of our preparation as well. We want to do, like what we said earlier, we want to do the LC preparation, and we want to do the test run. For example, if you say you quench the acid because you don't do aqueous, you don't do your typical benchtop workup, you do this unique one just for our screening. You want to make sure everything will work as planned. So you do develop, LC, shorter LC if possible, and then you do have a different workup. And the test run, especially for newer chemistry, you don't know. And then you work up the whole thing. You do the whole thing from beginning to the end. And then when the data come out, should be maybe not exactly the same, but it is comfortably within the range of your comfort. And then after all that, we do the whole play. Even with that, a lot of times the whole plate will have different situations because now you have 96 different conditions, 96 different bases or different variables that you will observe it during your play run, and then that's okay. Then you learn it, and your follow-up plate you just do it accordingly. So it's never a foolproof everything will work as planned, but you just always learn from previous steps.
Okay, next question is, how did you dispense sodium hydride in your plate?
Oh, this particular case, we actually don't do the sodium hydride. We actually pre-made this. This actually is the only time we use sodium hydride. We actually pre-made this, the stock solution, and it's actually a solvent-soluble thing, so it's become a liquid addition. Because everything we do run is in the hood, I can imagine if you want to dispense it, we'll have to test it. Is if you want to just do slurry dispense, it's possible. But in this particular case we talk about, it's actually done pre-screening. We actually prepare a stock solution. It's actually a solution, and I think what you think about the sodium hydride issues it's not in this case. It's not an issue here because we actually just add through liquid. Okay,
and our last question from the audience, how often do you find that you are custom designing each plate for a first pass screen versus using a standardized template that has been previously customized for a general transformation type, such as Sturckley, Hinder, Suzuki coupling reaction?
So, okay. A lot of times it really depends on the reaction transformations. Certain type of chemistry, the chemists who want to screen it know exactly what they want to do. They gave me just 96 conditions, hopefully not all different reagents, which will be, hopefully they're, common variables so we don't have to prepare too many stock solutions. So a lot of times what happened is people gave us general ideas, and if it's for a common, like what you said, maybe it's for a common transformation, we'll give them common, like phosphine ligands or common catalyst precursors, have a common play setup. And now we have a conference call, and then we'll talk about, is that something you want to see, or there are certain variables you actually want to see is not included. So we kind of, we provide the options, and then we have a conclusion after the, the finalized design is after it kind of both sides understanding what we're getting into.
Okay, that concludes our question and answer session. If you have any additional questions regarding the seminar topic, you're welcome to contact Pu directly. His email address is pu.sun, S-U-N, @freeslate.com. Again, on behalf of Freeslate, thank you very much for your participation in today's webinar. Have a good day. Bye-bye.